The idea is if you've got a curve and a line and they're tangent, then near this point, this is the point of tangency, if we were to look at this area right in here, we would see that the function and the line are very close to each other. And in fact, the closer we get to that point, the less indistinguishable they become. The key in all of this is that functions can be approximated by lines. And lines are easy to work with, right? Just a straight line. Functions can be complicated. Parabolas or cubics or cube roots or to the fourth powers or sines or cosines or logs or any of the complicated functions that you got. These may be hard to deal with, but these are easy to deal with. So tangent lines have a big application in calculus. Here was a problem that was on the AP test. F is twice differentiable. That says f of 2 is equal to 1. It also says f prime of 2 is equal to 4. And this says f double prime, if we needed that, was equal to 3. And the task is, what's this approximation? What is f of 1.9 approximately equal to, right, using the tangent line to the graph? So it's a pretty straightforward one if you know how to find the tangent line to a graph. So what we want to do is we want to say this function is about the same as the line. Now, when we go into problems like this, the key on this tangent line is to know two things. You need to know the slope, which is obviously a derivative, the slope of the tangent line, and you need to know this point, which is typically written as c comma f of c. There's a nice illustration in your book, page 190 if you're looking there. Okay. So the thing that you need to take away from this is that the tangent line approximation is equal to this. It's the y value plus the slope at that point, that's going to be a number, times x minus c. And if you just remember that, whenever you need a tangent line, you just write that down, and then you're done. Now, you may have to calculate the slope, but in this first problem, we don't have to calculate it. It was given to us. So here's the problem again. It tells you f of 2 is 1, f prime of 2 is 4. Notice that this is m tan. This is the slope of the tangent line. Right? And they want the tangent line at 2. So we'll just write down what I had just a second ago. L of x is equal to f of c plus f prime of c, x minus c. Just like product rule, quotient rule, chain rule, any other rule that you're doing, you should probably have this thing memorized, if not by today, but certainly by tomorrow, so that you can pop it off in a hurry if you need it. So here's our tangent line for this problem. The point was 2, 1. Right? This is the ordered pair 2, 1. F of 2 is 1. So I'm going to put 1 there. That's the y value. They told me the slope, that was 4. And then I put x minus 2. That's the line. Okay, the y value, right? This is f of c. The slope. And then this x minus 2 is the x minus c. Now, not to make this like a mystery, you did this in Algebra 1. You did this in Algebra 1. No, I didn't, Mr. Bosque. Yes, you did. You just called it different things. If we had a line with a point in it, 1, 2, and I told you the slope of the line was 4, and I said, what's the equation of that line? You knew it was y minus y1 m times x minus x1. That was called the point slope form of the line, and you would have written y minus, this was 2, 1, sorry. 2, 1. You would have written y minus 1 is equal to 4 times x minus 2. And your teacher would say, fine, I like that. Or the teacher may say, hey, I want you to get it in slope-intercept form. You go, okay, teacher, I'll add the 1. So then you put the 1 on this side, and then you have 4 times x minus 2. And the teacher would say, okay, keep going, get it y equals mx plus b. Yes, ma'am. So y is equal to 4x, and then what's that? Take away 8 plus 1 is take away 7. And that would be the equation of that line. Well, don't you see this is exactly what we're doing? The slope is the f prime of c, f prime of c. And this point here, this is the f of c. Right? So when we say our tangent line, this y guy, is f of c, that comes from here. That's the y1, that's the y value. Move it to that side. And then the slope, which is f prime of c, and f minus c is this x minus x1. It's just a point slope form of a line, not really calculus. Okay, so let's just finish this problem, and then we'll go over the ones that you did yesterday. We want the tangent line approximation. Well, I wrote down the tangent line. I guess I'll do it again. F of x is about the same as L of x. So f of x is about the same as, what do we got? 1 plus 4 times x minus 2. This, I don't even know what the function is. They didn't tell me, but it's about that. And they want f of 1.9. F of 1.9 is approximately, figure it out. Put 1.9 in there, here, and here. Just put 1.9 right there. Okay? This one? It's got to be one of these answers. F of 1.9. So 1 plus 4 times 1.9, take away 2. Yes? Which is equal to 1. This is 4 times a negative 1/10, right? Which is equal to 1 minus 4/10, which is 0.6. There it is, 0.6. Okay? Pretty, I mean, as long as you have the tangent line, you're done. Try this one. F is a differentiable function. F of 3 is 2. F prime of 3 is 5. Write the tangent line to the graph. I mean, again, you're going to start off, f of x is about the same as L. Go ahead and write down what L is. It's about the same as L. I give you the point, I give you the slope. Once you have that, try to find an approximation for the zero of a function. Now, you sort of have to remember, what is the zero of a function? Zero of a function. Anybody want to drag that out of their algebra memory or pre-calculus memory? X-intercept. Could you elaborate? Say again? It's not the y-intercept, it's the x-intercept. Y equals 0. Okay, so any one of these mean the same thing, right? The zero of a function, where y is 0, it's the x-intercept. Go ahead. You got an answer? Anybody? It's got to be one of those 5. See? Okay, how'd you get it? What's your line? Who said C? What's your line? X minus 3. That's a tangent line. Okay, now what'd you do? Where did you go from here, I guess is the question. Yeah, you make this equal to 0, right? So 0 is equal to 2 plus 5x minus 15. So what's that? 15 subtract 2 is 13. 5x, right? So x is 13 fifths, 2.6. Okay? Yeah, that one you had to know what a zero of the function was. Here's one more I found. They have these about every few years. This is some weird graph. It says the function f is defined, the graph of the derivative above. And the task is 3, 5 is on the graph. Now, as soon as you read that, you should be clear what's going on. 3, 5 is on the graph of f. When you look up here, that's obviously not f. Not f. Right? This is f prime. This is the derivative graph, not f. Don't have f. Don't know what f looks like. But what they ask is, what's the equation of the line tangent to the graph at 3, 5? And it's got to be one of these 5 choices. I think you could get it. Barely get it on there. Okay. So write down the equation of the tangent line. Put in all the information you know. And then see if you can pick one of those 5 choices. I gave you the point, 3, 5, so that's easy. This is 5. This is 3. This is supposed to be f prime of 3. How much is f prime of 3? 2. Don't you see that on the picture? F prime of 3 is 2, right there. Okay, so that number is 2. And then go ahead and play with that and choose one of those choices. Which one we like? See? Yeah, here they've actually moved the y over, right? So this is y, and then put the 5 back over here. X minus 3. Okay, so these are sort of trivial applications of tangent lines. Yesterday I gave you a number of different problems to play with. I want to make sure you're comfortable with those. You need to come up with like 5 different approximations. We'll do them, make sure that you're okay there. And holler up if you don't like anything. This first example I gave you was the square root curve, a real quick sketch just to sort of get your brain in the picture here. This is the square root curve, and there's a point on the square root curve, not to scale here. This is 110, right? So the ordered pair 100, 10. Square root of 100 is 10. We know that. And here's my function, f of x, square root of x, and I draw the tangent line right there. And our task is to use the tangent line. We're going to come up with the equation of the tangent line in just a minute, right? And then use the line to approximate the square root of things. Like we were supposed to use the square root of 100.37. Okay. So first, let's get the tangent line. Here's the equation of the line again. We need the y-coordinate, which is 10. We need the slope of this green line, which isn't hard to do. Here's the derivative. It's 1 over 2 square roots of x, but I can't use that for a slope. That's not a number. So I have to evaluate it at 10 or at 100. So you put 100 in here, so you get 1/20th, right? Okay, so evaluate it. It's 1/20th. That's the slope, 1/20th, and then x minus 100. Okay, so that's the equation of that green line. Okay? And then once you have that done, you can use that to approximate square roots. So if we want to approximate the square root of 137, we've got the square root function is about the same as this guy right here, 10 plus 1/20th times x minus 100. And you want to put in a number like 137, you can do that. 100.37 is about, you just put 100.37 there, and it's not too bad. 100.37, take away 100. And I've worked it out there, and you get that decimal. When I did this on my calculator, that's what I got. So, I mean, if you just compare the places, we know it's a little bit more than 10. There's tenths, hundredths, thousandths, 10,000. I missed it by just like 200,000. Pretty close. You know, this is as best as the calculator you can do. This is more accurate. More accurate. Is my approximation too big or too small? Too big? This is my approximation right here. Right? Is that too big or too small? Look at what the calculator says. Do we agree it's too big? Okay, look at the picture. Does it make sense that this tangent line is going to be a little bit too big? Why? Above the curve. The curve's going this way, the tangent line's going that way. Okay, easy. The second example was to approximate this, right? And again, if you just draw a little sketch, you can sort of get a sense. There's the curve. There's the line. Is my approximation going to be too big or too small? Too big, why? Tangent line's above the curve, right? Okay, so you go through all the steps again. This is what we get by using the tangent line. That's what my calculator gave me. So yeah, the approximation's a little bit too big. Okay? Comments on those guys? And now, we want to approximate the square root of 50. First thing we should do is find the equation of this tangent line. Once you do that, then you should have a good approximation. Okay, so the tangent line is going to be the y-coordinate, right? And then the slope there, the slope of that tangent line times x minus the x-coordinate of that point of tangency. And I said we should use this point. In the other two examples, we used 110 because the numbers are close to 100. But this number is not close to 100, so it would be dumb to use the other tangent line. It would make more sense to use this one. Okay? So L of x is equal to, what goes here? 7. Okay. Slope, 1 over 14. And then x minus, not 7, 49. 49. 7 is the y-coordinate, right? 7 is the y-coordinate. That goes there. Or sorry, 49 is the, 7 is the y-coordinate. That goes there. And 49 is the x-coordinate. That goes there. Right? Okay. So once you have that, then you can easily write down the equation. The square root of x, the square root of x is about equal to 7 plus 1/14 times x minus 49. Now, in my morning class with my discrete math folks, I mean, I'm really struggling just to get concepts down. So if I say, what's the square root of 49, I think I could get out of them the number 7. And if I say, what's the square root of 64? No problem. They say 8. Got it. If I say, what's the square root of 50? They're going to look at me and go, I don't know. And then I'm going to say, guess. I don't know. Well, it's square root of 50. Don't we agree it has to be between 7 and 8? And has slightly more than 7, right? Closer to 7 than 8? All this does is it gives you a nice way of doing that. Right? It gives you a tangent line approximation. There are other ways to approximate it. Square root of 50 is about 7. We knew that. But we're going to add a little bit more. This is how much we add. We're going to put 50 right there. 50 minus 49 is 1, so that's 1/14. There, 7 plus 1/14. That's our approximation. That's the tangent line approximation. 7 plus 1/14. If you do that on the calculator, here's my magic calculator. Square root of 50 is 7.071. Now, it's obviously irrational. It goes going to go on forever. That's as best as my calculator can give me. That approximation's right here. What is 7 plus 1/14? Well, 7 plus 1 divided by 14 is that much. 70714. So we're off, right? Our approximation's a little bit too big. The more accurate value is down here. Square root of 20. We need a point on the curve close to 20. Well, there's a point on the curve. So we'll do that one first. Equation of the line, y-coordinate, 5. I need the slope. Well, I actually told it to you. It was 1/10. Now, it does say you should verify that the slope really is 1/10. Don't take my word for it. So let's see. F of x is the square root. Here's the derivative, which is 1/2 square roots. And the derivative at 25 is 1/2 square roots of 25. And 1/10 there. Okay, so that works. And then x minus 25. That's the equation of our tangent line. So the square root of x is about 5 plus 1/10 times x minus 25. Okay? The function's about the same as the line, and you're trying to figure out the square root of 20. So just chuck 20 right in there. Square root of 20 is about 5 plus 1/10 times 20. Take away 25. Right? What do we get? The square root of 20 is about 5 minus 1/2. Right? 4.5. Make sense? I mean, I would hope. We know the square root of 25 is 5, so the square root of 20 has got to be something smaller than 5, because 4.5. Now, I noted in this problem that you could also use this point, right? Now, which one's better? I'm not sure either one's better. I might want to do something else, but if I'm using a tangent line, I need a point close to 20. And 25.5 is close to 20. 16.4 is close to 20. So we'll do the whole thing again a different way and see whether or not we get another approximation. Okay, so now our tangent line is going to be 4 plus 1/8 times x minus 16. And I'm using a different point. And again, you should verify that the slope really is 1/8. It is. Okay, so the square root of x is approximately 4 plus 1/8 times x minus 16, which means the square root of 20 is about 4. Plus something, right? Plus, what? 20 minus 16 is 4/8, right? Back to the half again, so 4.5. Now, neither one of those are right. You know, here's the best. The calculator can give me the square root of 20. But 4.5 isn't bad. I mean, I missed it by 3/100. Okay. Well, we always deal with square roots. No. Oh, I need to approximate the cube root of 9. So the first thing you do, I need a point. Here's a point. Here's a root function. It looks like this. Okay, and here's a point, which is 8.2. And I'm trying to approximate the cube root of 9. 8.2 is on the curve. There's 8. And 9's pretty close to 8. So the hope is if I can come up with this tangent line, and I'm trying to figure out the point, right? I want the black dot, but I'm going to use the green dot. Okay. So once again, the function is close to the line. So here's my line. It's the y-coordinate, which is 2, plus the slope. Let me leave that open just for a second. X minus 8. And you do have to calculate the slope. Now, in this case, f is x to the 1/3, which means the derivative using the power rule is 1/3 x to the negative 2/3, right? Okay. And we're supposed to evaluate that at 8. So f prime at 8 is 1/3. Now what do we do with this guy? Well, I would throw it down, so that becomes 8, and then make this positive 2/3. So that's the cube root of 8, which is 2. 2 to the second power is 4. 4 times 3 is 12. 1/12. Okay. So again, well, yeah, but it did say verify it. I mean, don't just take my word for it, because in the other two, you're going to have to do it yourself, right? Okay. So we just put 1/12 there, and then approximate this cube. So you do all that work. 1/12. Okay, so the cube root of x is about the same as 2 plus 1/12 times x minus 8. That's a tangent line to the cube root curve. It works really well. This is a good approximation for x numbers near what? See, now we're back to the discrete math class again. What kind of numbers can I put in that this is a good approximation for? 8, numbers near 8, right? Numbers near 8. In fact, if you put 8 in there, it's not an approximation at all. If you put 8 right there and 8 right there, what do you end up with? Cube root of 8 is 2. I know that. Right? This is good for numbers near 8. Like 9 is what we're supposed to do. Cube root of 9 is about 2 plus 1/12 times 9 minus 8. Right? So it's about 2 plus 1/12. And again, if you want to, what does 2 plus 1/12 look like? You could do that pretty easily. 2 plus 1 divided by 12 is that decimal. Here's what my calculator said. Okay, so are we close? Yeah, we are close, right? This says 2.083, and this says 2.080. So we missed it by 3 thousandths just by using the tangent line. So right? Okay, next one. Take that thing and raise it to the 4th power. Use a tangent line to do it. We're going to be using this point on the curve, 216. This is a quartic. The function here, f of x, is x to the 4th, And what we want to say is x to the 4th is going to be about the same as a line. Now, the task is, what's the line? Do we have a y-coordinate? Which is 16. Do we have a slope? Well, I said the slope was 32. How do you get to that? Where did that come from? Well, you're going to have to take the derivative, which is 4x cubed, right? And then put in 2, right? So this is 4 times 8, 32. That's the slope. X minus, this is good for numbers near 2, right? X minus 2, good. So this 4th power equation now is the same as the line, and lines are easy to work with. Right? So x to the 4th is about the same as that, which means if I took 0.13 to the 4th, that's about the same as 16 plus this other stuff, 32 times 2.013, take away the 2. Yeah? And that's not terribly bad. Let's see. 2.013 to the 4th is about 16. Duh, I know that. 2 to the 4th is 16. 2.013 to the 4th is about 16. We have to add, what is this? This is 13 thousandths. So we're adding 32 times 13 over 1,000. That's how much we're adding. Right? And if I want my calculator to sort of add that up for me just so I can get my approximation, according to this tangent line, it's about 16 plus 32 times 13 divided by 1,000. Okay, so there's my approximation. If I actually take that and cube it using the, or raise it to the fourth power, I get 16.42. I've got 16.416. So I was close. Is my approximation too big or too small? Too small. And so why would that be? You know what the graph of y equals x looks like. It sort of looks like a parabola. Like that. Yeah? And if we have a point, is the tangent line above or below the curve? It's below the curve. So the tangent line approximation is a little bit too small. Yeah? Okay. Any questions on tangent line approximation? In engineering, there's a commonly used approximation for the sine function. The sine function is about the same as x. Sine is about the same as x. But that doesn't make sense. Okay. The sine function does this, and x does that. How can they possibly be the same? Well, let me just show you. Let me pick a number. How about the sine of, I don't know, 0.0127. And that works out to be 0.0157, 0.015699. Aren't those pretty close? Yeah, they really are. It's like the sine of x is about the same as x. Oh, wait, that can't be. Let me try the sine of 2. Well, that's nowhere near right. I mean, that's crazy wacko, right? That's just wrong. So I guess the question is, why and for x values? Well, here's my function. F of x is the sine of x. Here's the picture. You know what it looks like. Let's pick a point on the curve. Well, there. You could choose a point somewhere over here, but if I draw a tangent line there, you know, that's obviously just a horizontal line, y equals 1. Give me a point on the curve. You said 0, and I jumped down your throat because that's not a point. 0.0? How about 0, 0? Do we agree that's a point on the curve, the origin? Okay. Let's draw the tangent line at 0, 0. By the way, anybody want to take a wild guess what the equation of that tangent line is? Y equals x. Yeah, y equals x. Yeah? Here's my tangent line. I need the y coordinate. 0. I need the slope. Where do you get the slope from? No, you don't get the slope from a y-intercept. Our function is the sine of x. Where do we get the slope from? The derivative. You have to take the derivative. This is a calculus class, after all. You would expect derivatives to show up. Cosine of x. And I can't just write cosine of x. I need to put in a number. Because the point is 0, and the cosine of 0 is 1. Okay, so that's 1 times x minus 0, the x coordinate. So sure enough, our line is simply x. The sine of x, this function, is about the same as the line. Now again, for which x values is this good for? Well, it's exactly right for 0. You don't have to say the sine of 0 is 0. So what type of x values is it good for? Numbers close to 0 is the answer that makes sense. It doesn't have to be numbers less than 1, but numbers close to 0 makes sense. Okay, so this is good for x values near 0. It makes sense. That's a standard approximation. Okay, now let's jump back in text. The other thing I asked you to do yesterday was to do some of those differentials and indefinite integrals. I just want to agree on the answers. We're going to start formal integration tomorrow. This little side excursion into approximations is the beginning of chapter 12. The beginning of chapter 12. In fact, just for a minute, look on page 605. You guys have books 605. This is chapter 12. We're going to do this mostly in April. And most of April is going to be in that box there where it says f of x is equal to f of a, right? And then it says f prime of a, x minus a, and then it has some other stuff after that. And in fact, it has an infinite number of terms. Are we supposed to remember them all? Yeah, you're supposed to remember an infinite number of them. That's an exact statement. That's an exact statement. If I take away some things, it can't be exact anymore. Right? It can't be exact. If I take away these guys, what's that? What's it called? Tangent line. This is L, right? So f of x is about L. Isn't that L? Yeah. A tangent line is about an approximation for a function. If you want the exact value, if you want this to be equal, you got to add a bunch of stuff. So it becomes exact. Right now, we're just doing the very, very, very first part of Taylor series. It's not going to be exact. It's going to be approximate because we don't have the right Taylor. Okay. Okie dokie. So yesterday in class, you did a little bit with the differentials and the indefinite integrals. Let's just read off answers so that you're good. Hopefully you were checking these in the back as you went. These were on page 196. 196. I said 9 through 25, the odds. Any questions on those? I think you did that the night before. 1 through 25 odds. Okay, and then 27 through, where did I take you up to? 30, 39? Okay, so 27 through 39, 27 through 39. These were odd problems that you did in class. I don't know how far you've gone through here. Let me sort of step you through the first couple. 27, it says dy is equal to 20x cubed dx. My suspicion is what most of you did was this. You put the dx back over here, so you had the derivative was 20x cubed. And then you said, oh, that's like those quickie problems, right? The derivative is that, so now I can figure out what y is. I had to make that the fourth power, divide by 4, right? So it was 5x to the fourth plus some constant. And that's probably the way you did that, which is fine. There's probably a more formal way of doing it we're going to see tomorrow. Let me just introduce it now. You don't have to go through this step. In fact, it's usually a waste of time. Instead, you do this. Now, you can see that notation yet, right? This says the antiderivative of the derivative of y. The antiderivative of the derivative of y. This is y. Yeah, that just works out to be y. And this says, give me the antiderivative of 20, which is 4x, or 5x to the fourth, right? 5x to the fourth. Now, we're going to have some very specific ways of doing this over the next couple of days, but any way you worked them out, I would have been happy. 29 dy is sine 4x dx. Right? And so you probably threw the dx over, and you had this derivative, and you remembered that when you take the derivatives of trig functions, the angle never changes. So there had to be a cosine in here, cosine of 4x, but that didn't work because there would have been a negative. So you had to put a negative, and that didn't work, so you had to put a 1/4. And you did all that, right? And then you added your constant, okay? By the way, I'll embarrass everybody right now. How many people lost at least 1 point because they didn't put plus c? Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You better put plus c. I'm taking like 6 points on yours. Okay, 31. 31. It has dy 0.5 x minus 1 to the 6th. Okay, so this is sort of a challenge now. Here's the derivative. It's 0.5 x minus 1 to the 6th. And the task was, what was y? Well, we know we subtract 1, so I suspect that there was a 0.5 x minus 1 to the 7th, which is a good start. But that didn't give you the right answer. So, okay, 1 over 7, that's a good start, but still doesn't give you the correct times 2. Okay, so let's, yeah, there's obviously a constant in all these. What you might want to do is try doing this. See whether or not you get this answer. You will. That is the right antiderivative. More tomorrow. Try some of the even problems in this problem set. Try even. Okie dokie.